there. So the next speaker is Stefan Knecht, who's going to talk about relativistic quantum chemistry and exact two-component Hamiltonians. He's already sharing the screen. Can we hear you?
Yeah. So can you see my screen? Okay.
Okay. Perfect. So, yeah, you can go ahead. 20 minutes.
Okay. So, thanks, well, Stefano and Roland and Ignacio for putting together this really nice conference. And yeah, so as my title suggests, this now goes a little bit different as the usual open MOCA stuff. But in the end, I hope you can see a connection to open MOCAs and how this development could actually be useful. So the thing I will be talking about is actually spin orbit corrections for two-electron Hamiltonian or for well, electronic Hamiltonians, for exact two-component Hamiltonians, and how that actually can also be useful for open MOCAs. And the general theme of my research has always been like, I'm always interested in, say, being able to describe the entire periodic table of elements. And as you can see, this this periodic table is really, well, quite amazing if you think about, I mean, what can you do with all these different elements? And here it's sketched, so most of the elements are actually find their use in daily life. And one of my favorite elements, and it's not only me, it's actually mercury. And so mercury has a particular property, namely that it is liquid at room temperature. And well, if you're probably as old as me, or maybe a bit older, you know, in your childhood days when you were sick and you wanted to check the temperature, or your parents wanted to do that, you had the thermometer, and probably it was with some liquid in it, and most likely it was actually mercury. These days it's no longer mercury, but if you find a liquid thermometer, then it's probably a mixture of gallium with some other metals, so that it is actually liquid at room temperature, because mercury is the only elemental metal liquid at room temperature. So there's also cesium, which is slightly above room temperature, and gallium. But if you mix gallium with other metals, then you can actually make it liquid at room temperature. And so the chemical symbol Hg for mercury comes probably from the Greek hydrogyrum, which actually means liquid silver. And so the question is, I mean, what chemists have been trying to answer for a very long time is actually, why is mercury liquid at room temperature? And thanks to the tremendous efforts of Peter Schwertfeger and his research groups and many colleagues over the years, so roughly 25 years, that's time that that Peter spent on this topic, they actually could find out and found real evidence that the melting point temperature of mercury is really determined by relativistic effects, and to a smaller extent actually also by electron correlation. So in the end, so if you look here on the right, you can see that if you describe say zinc and cadmium, so the lighter homologs in the group 14 here, sorry, in the group 12. So then you can actually see that that it is a tremendous relativistic effect. So if you describe them non-relativistically, or zinc and cadmium, all is fine. But if you change the description for mercury, you get a huge effect, and that's about 161 Kelvin. And so if you want to be able to describe, say, the properties, the molecular properties, elemental properties of all the elements that you have in the periodic table, we need to be able to describe both the electron correlation effects that substantially play a role in for the chemistry and molecular properties of any compound, if you wish. But we also have to think about how to describe them in terms of relativistic effects. So we also need to consider what kind of Hamiltonian do we actually want to use in our quantum chemistry simulations. And so to summarize this challenges that we have here, so of course there's the accurate treatment of electron correlation, as I said, and there are various methods out there, and I don't want to talk about this today. And so I just assume you pick your favorite method that you like, but then you're still left with the problem of how to include relativistic effects. And so there are scalar-relativistic effects and spin-orbit coupling. And just because I don't know how familiar you are with these terms, so let me quickly remind you what are actually relativistic effects. And I put it here in quotation marks because our world is relativistic. Okay, so this is relativistic effects are just really a hypothetical construct denoting the difference between a Dirac quantum mechanical and a Schrödinger quantum mechanical description of matter. Or if you like, in a classical sense, whether you use the Einsteinian principle of relativity, so special relativity, or the Galilean principle of relativity. Okay, so there's more or less a one-to-one correspondence if you use the correspondence principle to go from Galilean principle of relativity to Schrödinger quantum mechanics, or from Einsteinian going to Dirac quantum mechanics. So as a quantum chemist, we usually distinguish two kinds of relativistic effects. So there are kinematic or scalar relativistic effects. So essentially those that affect the kinetic part of the kinetic energy operator, and spin-orbit coupling, so sort of coupling between angular and spin momentum. So that's sort of a magnetic effect. And a different distinction that we sometimes use in chemistry is direct relativistic effects, meaning the contraction of S and P shells, and spin-orbit coupling and indirect relativistic effects. That is, because of the contraction of S and P shells, we get a better screening of the nuclear charge, and therefore the shells with the higher angular momentum, like the D and F shells, they tend to expand. Okay, so if you want to visualize this, for example, for the uranium atom, what you can see is on the left here, you have direct effects, namely, for example, if you look here for the relativistic pattern, you have a stabilization of the S shell in uranium, of the valence 7s shell, and you have the indirect effect, namely the energetic destabilization of the 5f and 6d shells, so that which go up in energy. And so I'm not sure you can see my mouse pointer, but somehow I'm quickly stopping here.
Here we see it, but in full screen we do not.
Okay, so I'm go here again.
Yes.
No,
goes away.
Can you see something now?
No.
No, okay, never mind. So for some reason it doesn't work. Anyways, so and on the right here, what you see is here you can see sort of the radial expansion and radial contraction of the shells. So the dotted lines are, now I can't really see it myself because I'm here on the screen. Just a second. Okay, I have to make this smaller here. So the dotted lines are the non-relativistic lines for the 7s, 5f, and 6d shells, and the solid lines are actually the relativistic ones. So you can sort of see it's most prominent actually for the 7s. You can see that the maximum of the solid line, the solid red line, moves towards the nucleus, and so it really contracts in a way. And so if we want to do relativistic quantum chemical calculations, we typically have sort of two ways of actually doing it. So either we include spin-orbit coupling and relativistic effects right from the start, and that we can do, for example, by using the Dirac Hamiltonian in a 4-component or in a 2-component, like electrons only form, which is sort of nowadays becoming more and more the standard of actually doing it, because there has been huge developments in the formulation of efficient 2-component Hamiltonians. Or another approach that is sort of very prominent in MOLCAs also is the two-step approach here on the right, where you include spin-orbit coupling by state interaction. So essentially you solve like a generalized eigenvalue problem where you first determine the Hamiltonian in the basis of eigenfunctions of your H0, where H0 can be a non-relativistic or scalar-relativistic Hamiltonian, and then you add the spin-orbit Hamiltonian on top of that and evaluate the sort of the coupling matrix elements for the spin-orbit Hamiltonian in the basis of the eigenfunctions of H0. And so this is essentially what you do when you invoke Rassi, right? So this is like the most prominent thing in how to include spin-orbit coupling in open MOLCAs. And so if you want to stick to a state two component Hamiltonian, then the typical procedure is as follows. So the sort of these days most prominent two-component Hamiltonian is to do an exact two-component approach, and that relies on decoupling the one-electron Dirac Hamiltonian, this small hd here, by using a unitary approach, also unitary decoupling, where I then end up with, say, this h tilde plus plus here and the h tilde minus minus, and you only consider for your quantum chemical calculations then the h tilde plus plus. And so you can do that quite easily in a finite basis set representation, because you can exactly diagonalize your HD and your Dirac Hamiltonian in a matrix representation, compute the unitary matrix that will decouple, so that will exactly diagonalize this Hamiltonian, and then you can proceed from there. And in principle, you would have to do the decoupling of the two-electron part in a similar way. But here you see you have to do two unitary transformations, because you have to do one for particle 1 and one for particle 2. And so you would end up with this 4x4 matrix of the two-electron operator. But as you can see, if you would like to do, and you would have to do this decoupling in every SCF iteration. So if you think about this, if you would require to do this in every SCF iteration, then your two-component calculations would be much more expensive than actually the four-component calculations. So that's essentially why nobody does this. But you just say, okay, I approximate my two-component two-electron operator by just taking sort of the upper block of the four-component operator. And the difference between this G4CLL that you see down here with respect to this exactly transformed G tilde plus 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 operator, that's known as a picture change error. Okay, and then the question is how to deal with this picture change error. You know it's there, and the question is how to make this error as small as possible. And in the past, I don't know, more than 50 years since the two-component methods have been around, there have been different models to sort of address the two-electron picture change effects. And one of them being a parameterized model approach, where you're based on the nuclear charge, you multiply your one-electron spin-orbit integrals with element and angular momentum specific screening factors if you evaluate your one-electron spin-orbit integrals. And that's most known as, or one of the most famous approaches is actually the Böttger factors. Okay, and then there are other approaches like the atomic mean field spin-orbit approach. And if you do this in a sort of first order sense, then this is what is called the atomic mean field integrals that were implemented by the late Bernd Schimmelpfennig. And this kind of approach is used very widely in quantum chemistry program packages. For example, open MOLCAs, it is used in Dalton, and it's used also in Dirac and many other program packages. I think QChem is actually as well. And then very recently, about 2 or 3 years ago, Lan Zheng proposed sort of an infinite order spin-orbit atomic mean field approach, which is much more superior to the Amphi model. But it has some, it still has some drawbacks. But this is another way. And then something that has been sort of promoted by Christoph van Wuelen within, for example, also the turbomole community, is to use atomic model densities within the framework of Kohn-Sham DFT. If you want to do two-component Kohn-Sham DFT calculations. And so we have been thinking about how to overcome some deficiencies with this Amphi approach that we have seen, for example, also in Dirac. And because it's, in the end, it's a first order spin-orbit coupling approach in a sense. And so we wanted to come up with a more robust and a sort of the best possible atomic mean field approach that we could think about. And so the guiding principle for us was we wanted to bridge a gap between a full molecular four-component and a molecular mean field exact two-component method. And molecular mean field exact two-component method means you solve first the molecular four-component SCF calculation, and then you use the converged Fock operator of the four-component of your four-component calculation to transform to two components. So you can imagine you still have to solve a four-component SCF problem. So it's not ideal, but it's at least better than doing a full four-component molecular correlated calculation in the very end. And so what we wanted to do is we wanted our method to comprise the full two-electron picture change error corrections. So that is, we wanted to treat two-electron spin orbit and two-electron scalar-relativistic corrections on the same footing. Okay, we wanted to be able to take into account the characteristics of the underlying correlation framework. So that means we want our corrections to be specific, whether we want to do Hartree Fock or we want to do DFT with a particular functional. So for example, if you think about Amphi, this is not possible with Amphi. So you have the same corrections no matter whether you do Hartree Fock or DFT. And if you do DFT, if you change your functional, you get always the same corrections. But that cannot be true. Okay. So we wanted to overcome this limitation. And we also wanted to be able to provide an approach that allows you to add also two-center, two-electron contributions in the molecular framework. In particular, if you want to do solid state calculations and you have periodic boundary conditions, this is something you will need. And we have come up with two independent implementations in two codes, namely Dirac and Respect. And if you want to read more about this method, here's the reference down here. And it's on archive and under revision in JCP at the moment. And so what is the idea? So never mind the many equations here on this algorithmic slide, in a sense, but the idea is, in our atomic mean field XTC approach, is we first have a loop of all unique atom types K. So that's in line number 3 here. And that loop ends in line number 15. So what we solve is we solve the atomic SCF problem. We compute the two-electron Fock matrix for in the four-component case, and we assemble that one in a molecular Fock matrix, which is in line 8. And then we also compute a sort of a correction term, so a two-electron Fock matrix correction term, which is stored in a molecular basis in line number 14. And then we can use the sort of the assembled four-component two-electron Fock matrix. We can use that in a molecular calculation. For example, in line 18, if we evaluate now the molecular decoupling, XTC decoupling matrix, we can add already some two-electron corrections to this evaluation. And because it's atomic blocks, it's still easy to solve this problem in line 18. And based on that, we can then solve the two-component SCF equations with our corrections terms. And this correction term is in the static term, the second one on the right. So this delta F tilde two-component two electrons. So that's a sort of a atomic correction term that is added in all the SCF iterations. And then we also came up with the extended version, where essentially instead of calculating atomic Fock matrix contributions, we actually calculate atomic density matrices in 4 and 2 component form and store that one. So that's this D4C plus that you see on line 10, and the D tilde 2C plus, which is the sort of the assembled molecular densities in 4 component or in 2 component form from atomic blocks. And then we use these quantities in the 4 component decoupling step, and also in the 2 component SCF steps down here in, say, equation 25 or in line 25. So never mind the details, but so the overall idea is we want to assemble everything from atomic 4 component calculations and possibly atomic 2 component calculations, correct or calculate correction terms, which are then added in a molecular calculation. Okay, and now the question is, how does this actually perform in comparison to, say, the previous Amphi approach, in comparison to not doing any 2-electron spin-orbit or scalar-relativistic corrections, and also in comparison to the 4-component results. And so in our paper, we decided we want to study extreme cases in the periodic table. So we want to go down to the very end, and also to a part at the upper part of the periodic table, because that essentially sandwiches all the elements that you have, or all the compounds that you could imagine in a quantum chemical calculation. So looking, for example, at orbital energies and total energies of a Hartree Fock calculation for the organesson dimer. So organesson is element 118, so that's the very last known element of the periodic table so far. And so if you compare the first line here, you can see that our 2-component AMF X to C and EAMF X to C, so that's they compare very well to the 4-component Dirac-Coulomb result, not only for the total energy, but also if you consider all the different orbital energies that are listed here. So that's the inner core and the upper part here, and the valence down here. So at the end of the table, so epsilon 118, that's the HOMO of the organesson dimer. You can see we are basically spot on in terms of orbital energies, and all energies are given in Hartree here compared to the 4-component result. But if you consider Amphi, for example, which is the third column here, so the Amphi X to C, which uses Bernd-Schimmelpfennig's approach, you can see the total energies, you're pretty much off. So that's you're missing about more than 100 Hartree in the total energies, but also your orbital energies, in particular for the inner part, are pretty much off. So, and if you don't do any 2-electron corrections, picture change corrections, which is the first column here, this 1e X to C, you can see for the inner part, Amphi does not change much. So between the first and the second column, you have very similar numbers, but in the valence part, Amphi really does a decent job. And we can repeat, so now the table has changed, we can repeat the same exercise actually for DFT. And here we have chosen a PBE function. And this is just to show you, so also here we get a very good agreement between our 2-component and the 4-component reference data. And Amphi again is not doing particularly well for the inner core, but it's kind of okayish for the valence part. And if we consider spin-orbit splittings then in the organesson dimer, and we do this, say, for the 2p, 3b, 3p, 3d, 4p, 4d, and 4f shell, you can see here the errors with respect to the 4-component result. And note that the y-axis is actually on uses a logarithmic scale, and all the data is in electron volts. And the reason you can't see any green and red color for our AMF and extended AMF models with respect to when you consider the error with respect to 4-component results is simply on this scale, you cannot see it. So it's just doing amazingly well. And you can see also that for Amphi, actually the error depends also on the kind of correlation model that you choose. So you have a different behavior for Hartree-Fock, which is the picture on the left, and for DFT PBE, which is the picture on the right. So the orange bars, those are the errors for Amphi. And you can see Amphi behaves differently for Hartree-Fock and DFT. And that's no surprise because the corrections are always the same, no matter whether you use Hartree-Fock or DFT. So they're not specifically tailored to DFT or the actual functional that you use.
Stefan,
yeah.
Sorry to interrupt you. You are already out of time, so please speed up a little bit.
Oh, okay, okay. Then I will skip and maybe just show this slide. So that's the last numbers I wanted to show. And that's so here we calculated X-ray core ionization potentials. So it's not excitation energies, but ionization potentials. I'm sorry for that. And what you can see here, this is now for a gold complex and a copernicium complex. And what you can see is that Amphi has sometimes problems to actually converge, and then you cannot do any corrections. But what you can see in the lower part of the table for the copernicium compound is that if you consider, for example, the spin-orbit splittings in the L edge of, say, copernicium in that case, you not only have large deviations in terms of absolute energies, so now the energies are in Hartree again with respect to the four-component result, which is on the very right, but you also have quite a deviation in terms of the spin-orbit splitting itself. So, for example, with Amphi, you're off for the LH spin-orbit splitting of copernicium, you're off by almost 0.73 Hartree. So that's more than, that's about 15 EV, something like that. And with our models, with the AMF X2C method, you're pretty much spot on. So the error is well below so that's below 0.1 EV. Okay. And with this, I would like then to conclude. So what I hope to have shown is essentially that we have now a method available that allows us to provide atomic mean field two-electron picture change corrections that can be used in two-component calculations. And this should replace, for example, the popular Amphi approach. And the good thing is it works sort of for any one particle basis set. It can be also used for different two-electron operators, not only the Coulomb operator, but also Gaunt and Bright. And because it is very simple to calculate these corrections, they could actually be provided as a library based on an HDF file type, or because of the discussions yesterday, I think also there could be a way to extend this and make this available through the TREX.io data file format. And with this, I would like to thank the people involved in this work, so Mikael Repiski, Trond Sau, and Hans-Jürgen Jensen, my fellows at the company, and you for your kind attention. Thank you.
Okay, so we have time for a quick question, which has already been asked in the chat by Felix. So when you pre-compute the atomic contributions, how do you deal with open shell electrons and degeneracies?
Yeah, so in this case, so in Dirac, for example, we use something like the average of configuration Hartree-Fock in that case, if we have open shell electrons. And in the respec code, we actually have a Kramers unrestricted SCF code. So we can do either really unrestricted SCF calculations, or we can do restricted calculations using sort of a theoretical averaging of all different occupations in the open shells.
Okay. Yeah. So there's another question in the chat, but I'll let you reply directly. So we need to move on with the schedule. Thank you again. Thanks.